Hello everyone, my name is Michael and today, together with Sebastian and Steven, we are going to present our wireless temperature monitoring system using LoRa EASC1278 modules and ESP32 microcontrollers. In this project, we designed a long-range, low-power communications link capable of transmitting real-time temperature data from a remote sensor nowhere in very node. Our system is made up of two ESP32 LoRa nodes. One works as the transmitter and the other works as the receiver. The transmitter reads the temperature using an LM25 sensor and sends that value through the LoRa SX1270A module. The receiver captures the data and uses it to control a DC motor. This creates a small automated system that reacts depending on the temperature. We chose this project to explore the advantage of LoRa technology, especially its long-range communications and low energy consumption. Our purpose was to build a system capable of monitoring temperature remotely and reacting automatically. These types of systems are commonly used in industrial monitoring, smart agriculture, and environmental application.
Hello, I'm Sebastian. These are the main components of our project. We have two ESP32 boards, two LoRa's SX1278 modules, an LM35 analog temperature sensor, a DC motor with its driver and breadboards, jumpers, and power supplies. Each component plays a specific role, from measuring temperature to transmitting data and finally activating the motor. The transmitter node reads the analog output of the LM35 sensor using the ADC of the ESP32. In MicroPython, we convert the analog value into Celsius and then send in through the LoRa module. This node keeps transmitting temperature data continuous so the receiver can act immediately. The receiver node listens for incoming LoRa packets. When the temperature value arrives, the ESP32 decodes it and shows it on the serial monitor. The same node contains the motor control logic, so depending on the temperature, it decides the motor's direction. The control logic is simple. If the temperature is below a threshold, the motor rotates forward. If the temperature is above the threshold, the motor rotates backward or stops. This demonstrates how sensor feedback can automate physical systems in real time. We selected LoRa because it provides long-distance communication while using very light power. The SX1278 works with sheer spread spectrum, which makes the transmission more resistant to noise and interference. This allowed use to send temperature data reliably, even and long distance.
Hello, I am Steven. We note we programmed in MicroPython. Using the Tony 8, we create separation scripts for reading the sensor, formatting the temperature, ascending in the low LoRa, receiving to the data, and controlling the motor. MicroPython helps use this code clean, modular, and easy to test. our system decisively transmitted temperature data will days and the receipt rate immediately be changing the motor days. The communication remains stable during the test and the motor responded correct receipt temperature. During demonstration, you can see how the transmitter sends temperature up constantly and sound as the temperature change, the receipt styles the ball and activates the motor accordingly. They provide the correct information, the system and the coordination between bit nodes. To conclude, this project shows how LoRa technology uses P32 microcontrollers and analog sensors can work together to create a remote automatic monitoring system. It is low power consumption and long range communication make it stable for many real applications. Thank you for watching and presentation.